Okay, everyone, this week is an intense week. Take a breath, don't get too freaked out. Next week is a little bit interesting and we learn some new topics, but then after that, the weeks are very easy. I've crammed all of your hard stuff towards the front of the term because I know you're going to get slammed in all your other courses towards the end of the term. So know that you're almost over the hump in this class so that you can kind of take a breath and relax throughout the rest of the term. There'll still be work. There's still stuff you have to do, but it might not be quite as challenging. So today, we're going to go the next step beyond what we learned last week. Last week, we talked about having 3 equations to solve for 3 unknowns to prove something that's in equilibrium. And this week, we're going to introduce something called method of sections. 2 things I want to address before we jump into that. The first is that I solved my sound problem and then it came back and then I spent hours solving it again and it was glorious. It worked. When I recorded my other lecture, I had no problems. It was perfect. I set back up today. I plugged in. I had no problems. I tested it and then just to double check, I recorded one more quick video and it had the problem. I did nothing different and then recorded 15 more that did not have the problem. So I cannot understand I tried moving around, I tried moving the mic. I don't know what is making that double echo and it's making me lose my mind a little bit. So I have thought of everything I can. If anyone else is like a tech genius and records a lot of videos while having multiple applications open doing multiple things, happy to hear your feedback. But I'm trying to see my screen because I need to be able to see the lectures and the advanced slides. I have my recording screen, I have my camera, I have the microphone, I have software for recording, and then I have other software for blending the videos together when I need to. So this is not my forte, but it's what I've figured out. The next thing I would like to address briefly is National Truth and Reconciliation Week, and very specifically day. For many of you watching this, it is September 30th. I'm recording it on the 29th, but I would be remiss if I didn't address this very important topic. I know many of you aren't from Canada, and there are quite a few of you that are. I'm sure it's going to be discussed in all of your classes, but National Truth and Reconciliation Week is acknowledging what the settlers of Canada did to the Indigenous people and the atrocities, not just the overt atrocities, but even the more subtle ones, the slow dismantling of a culture and an empire. And as somebody whose heritage comes strongly from the settlers, that is something that I need to acknowledge and understand my part, how repairs can be made there. I also have heritage that is Indigenous, not a lot, not much, and I am certainly not somebody who has suffered because of it. There are many more people, specifically families that experienced residential schools, which is, I know, the main focal point of most of the things being discussed for National Truth and Reconciliation Week, but it is by far not the only. It is maybe one of the most atrocious and maybe the most immediate. But I grew up in Nova Scotia where there was systemic racism against Indigenous peoples. I know that I've seen it and experienced it as a witness. I like to believe that I'm the person that would always step in and do what I can, and when things were extremely overt, I have. But growing up when I did, there were things that I didn't even realize were as racist and horrendous as I think back on now and realize I could have done better. I could have been a better person. So that's just something I really, really wanted to address. I don't have an orange shirt, and everything is sold out here because I refused to just buy an orange shirt on Amazon that did not come directly from Indigenous artists and where proceeds went to Indigenous kind of holdings. There are things engineers and architects can do. I don't have a lot of place to talk about that right now. I do think there is reading that can be done. I know that I do some lectures that rely heavily on some kind of forms and functions that were partially derived from indigenous structures. Not only from indigenous structures, but there was kind of a parallel between European and indigenous construction that were happening in parallel that I've seen combined recently. And I do a whole lecture series, or a lecture that I've done in Australia and Helsinki and in Florida, I believe, on that topic. So let's move on to this week's lecture. Last week, we talked about the fact that what we want is for things to stay still. We're talking about static equilibrium. They are staying still. If they're in static equilibrium, they are not moving in all 6 degrees of freedom, up and down, side to side, in and out of the page, and spinning around all of those axes. It is not moving. It is not doing those things if it's in equilibrium. Or what we're saying is that the sum of the forces and the moments along or about those axes equals 0. We find it easier to work in a 2D world, so we break it down into one plane. Specifically, we usually use the XY plane, and we say that as we study this problem, if it's in equilibrium, the sum of the forces in the Y direction must be 0, the sum of the forces in the X direction must be 0, and the sum of the moments about the Z axes must be 0. And if those things are true, it is in equilibrium. Well, we know our objects have forces on them, and we want to figure out what it takes for them to be in equilibrium, or we want to solve for the reactions. So, if we know that it must be in equilibrium, we can figure out what the reactions must be for it to be in equilibrium. And that's what we did last week. What happens, though, internally in those elements? We looked at some objects that had loads applied at a point out at the tip of a diving board, for example. And we knew there was a reaction back here that was holding the back end of that diving board back down. Well, what happens along the length of that diving board? There's a load out here, and there's a reaction here, but there must be something happening within the diving board. We know that our object isn't moving up and down, back and forth, or spinning about our z-axes. And so we need to find out what is happening inside our object, knowing that is the case. So if we found the reactions that keep that object in equilibrium, maybe we can figure out what is happening internally in that object. So last week, for example, we had this truss right here, and we wanted to find out what it took for this object to be in equilibrium. So let's do this one quickly, just so we can have a starting point to talk about. So we will use this to find the reactions, and then we'll talk about how to find out what's happening from this 10 kilonewtons to get to these reaction points. Okay, I'm just finding my notes so that I don't deviate from exactly what I'm showing you on these. All right, let's bring this down to look at my calculation pad, and I will make my notes larger. So we have a 100 kilonewton point load acting some amount over on this truss. I'm probably going to be going back and forth taking my sweater on and off. It's that funny time of year where you're neither hot nor cold, yet both simultaneously. Okay, let's start. We want to solve, Dave has used that pen and ruined it on me. Here's my good one. Okay, we want to solve the truss for its reactions. All right, let's draw a free body diagram of this truss. I'm going to draw it big this time. I'll probably draw it smaller as we get into this a bit. Okay. Look at this. We have a truss here with an applied load of 100 kilonewtons. We know that this is, well, let's write it in. It told us that there were 4 bays at 2 meters each. 2 meters. And that this is 3 meters. We want to figure out what the reactions are on this. All right, our X, our left, and our right. Before I do a thing, I want to think about what I think is going to happen. If I had 100 kilonewtons in the middle here, we did a few examples last week where we intuitively understood that half of the load would go here and half of the load would go here. If my 100 kilonewtons is further this way, do you think reaction right or reaction left will be higher? And I think intuitively you understand that reaction right will be higher. So I'm just going to write this over here for myself. I think that reaction left will be less than reaction right. I'm just going to write that there as a little note for myself so that when I go back and finish it, I'll see if my numbers matched my prediction. Because we know that that should be bigger than this just by looking at this. If I sat further over on a table, my load would go closer to there would be more of my load on the reaction or the legs of the table that I'm sitting closer to. And so this is a nice check to figure out if what we've done mathematically is correct. So let's start by summing the forces in the x direction, where everything in that direction is positive. Well, we have our x, and we don't have anything else. Our x does in fact equal 0. Let's sum our moments about the z-axis, where everything spinning in that direction is positive, and we want the sum of them to be 0. And let's pick the part or the point that we're going to sum about. I've told you I'm pretty lazy, and I always do that point right there. All right, so I'm going to spin it about reaction left. I'm going to put my thumbtack right here to spin it about. Well, our R passes through the node, and to be a moment, you need a force and a distance. Our L passes through the node, and to be a moment, you need a force times a distance. Thumbtack here, we have our 100 kilonewtons going in that direction. Well, if I put my thumbtack here and push like that, you can see it is trying to spin the page in that direction. Well, if I use my right hand and curl my fingers in the direction it's trying to spin, my thumb tells me if that's a positive or a negative moment. My thumb is into the page, so that is a negative moment. So negative 100 times, and remember, a moment is a force times a distance, and our 100 kilonewtons is 2, 4, 6 meters away. We then have our R, which is pushing in that direction. If we put our thumbtack here, it's trying to curl my paper in that direction. I can use the thumb of my right hand to tell me that since it's coming out of the page, it's a positive moment. So I have positive RR times 2, 4, 6, 8 meters. I can rearrange this to solve for RR. 100 times 6, so I'd have negative 600. I'd bring it over here and divide it by 8. Let's plug that in. So we have 100 times 6 divided by 8 equals 75 kilonewtons. Now let's sum our forces in the y direction, where everything upwards is positive. We have our L going upwards. We have our 100 kilonewtons going downwards, and we have our going upwards, which we've already solved for, is 75 kilonewtons. We can rearrange this, and we get that RL is 25 kilonewtons. Okay, well, we've solved for our reactions. Let's check if that matches what our prediction was. All right, we have 75 is greater than 25, so it seems to match our prediction, and we feel pretty good about that. So this is what we learned last week. All right, so I just realized that I have my mouse not on a large view for you. Give me just 1 second and I'll adjust the mouse cursor. There is only large and tiny. As much as it shows up on my screen as varying in size, it only shows up on the recording software as either tiny or large after I pass the 50% mark on the mouse size. So this is the size the mouse is when we do our calculations, or when we look at the screen. Okay, so we solved for these reactions. That was last week's exercise. So we've solved for our Rx equals 0, RL equals 25, and RR equals 75. We know that this is in static equilibrium if these are the reactions. So whatever is holding this truss up better be able to resist 25 kilonewtons and 75 kilonewtons at those spots. If you're saying, what if the 100 kilonewtons is over here? Yep, that is something we would have to check, but that is a different problem. We would also then need that one to be in static equilibrium, so maybe 75 here and 25 here. But we have to solve one problem at a time. If you're saying, wow, that seems like you guys have a lot of problems to solve. Yes, we often have to do it where we imagine that 100 kilonewtons at any point along the top of this. So these problems can get much more complicated, but that's well beyond what you guys are going to do. I'm trying to show you the principles or the basics of how this works, and we're going to work with it in one location right now. Okay, before we can go any further, we talked about what a free body diagram looks like for the object as a whole. Let's talk about what an implied or a partial free body diagram means. So if we're talking about a joint right here, if we were talking about what's happening internally on these members, and we're talking about this point right here, if an arrow is pointing towards the point, it is saying that we are in compression. If the arrow is pointing away from the point, we are saying it's in tension. So if we imagine that instead of our point being right here, and we put it in some imaginary spot in the middle of the member, well, an arrow pointing towards that point is compression, and an arrow pointing away from that point is tension. So when we're talking about internal forces, away from a node is positive, and towards a node is compression, or tension. No, sorry, forget that I said negative. Pointing away from a node is tension, and towards a node is compression. We're going to bring in what negative means in a little bit. Okay, so here's where I'm going to blow your mind. If the whole object is static, it also means part of it is static. I'm going to stop for just a second. I want to double check something in my slides. Okay, I didn't like exactly where I had the placement of one of the slides in my lecture there, so I just moved it around a bit. I think it makes it flow just a little bit better. So we just talked about internal forces being drawn in a free body diagram, which we don't tend to do on an overall whole object. We're talking about all the things we're looking at acting on an object. Now we're talking about internal forces. So let's see what we can do with this. All right, let's go to the next slide here. Method of sections is a really awesome technique that I'm teaching you about this week that reminds us that if we've already figured out that the object as a whole is in static equilibrium, which means we've figured out what the reactions are to make sure this is in static equilibrium, then we know that no part of it is moving. Forgetting deflection, because that's something else. We're talking about this object moving up and down or back and forth or spinning in space. If I said this whole thing isn't moving, that means this little bit right here also isn't moving up and down or back and forth or spinning in space. You're saying to yourself, of course, that's just, why would you even ask that? Of course, if I'm sitting still, my ear isn't flying off in space. But just reminding ourselves that that is true allows us to do something really, really cool. And that is the use of method of sections. If we know this whole thing isn't moving, we know that when we cut it up, this also isn't moving. So we're saying that this isn't moving, but look, we have a reaction acting on this thing. So how could it not be moving? We know it's not. We just figured out that it wasn't moving. But this doesn't look to be in static equilibrium, and we know it must. So there must be something holding this part of the object in place. And we know that it's the rest of the object. My ear isn't flying off into space because it's attached to my body, and my body isn't flying off into space. So the rest of this object is what's holding it in static equilibrium. So there must be internal forces happening here that keep it in static equilibrium. But we don't know what they are. Well, it's the same way we didn't know actually what the reactions were. We figured out what the reactions were by the fact that we knew it had to be in static equilibrium. So what if we said, we don't know what they are, we know there must be internal forces here, who knows what the value of those are, that is keeping this thing from flying off into space. So we can make this cut and we say to ourselves, what could those internal forces be? We don't know. Let's try to figure it out. So we know that if we have something not moving in space, we have 3 equations that prove that that is the case. So if the overall object is in static equilibrium, which means not moving up and down, side to side, or spinning about our z-axes, we know our section must not be as well, and we should be able to make those same assumptions. So let's see what I'm talking about. So let's, how did I end up with a crappy pen again? Okay. Let's cut keeping the left side. Okay, so we're cutting this, keeping the left side of our truss. I'm going to draw it a little bit smaller than I did last time. Okay, we knew, because we've already solved it, that there is a reaction here of 25 kilonewtons and a reaction here of 0 kilonewtons. We have something happening internally in this, and we do not know what it is. We're going to say, we don't know what these are, but we know that there must be some internal forces in here. So I'm just going to draw some placeholders. I'm going to call it A, B, and C. I don't know what these internal forces are. I don't know if they're in tension or compression. We also need to put our dimensions in here. This is 3 meters. And this is 2 meters. We don't know whether these are in tension or compression. I am going to draw in tension, but that's just a guess. I don't know if they are or not, but if everything comes out correctly and I actually get a tension or a positive value, I will know I drew my arrow in the proper direction. Do you remember when we looked at reactions last week? If we got a negative number, it meant our arrow was supposed to be in the other direction. So if I always draw everything in tension, positive will be tension, negative will be compression. If we always guess tension. If I guess compression and I'm wrong, I'd get a negative answer, which means it's really in tension. That can start to be a real pain in the butt because then you have to always go back and check, did I guess tension or compression? So I'm giving you an easy trick to always know quickly if your element is in tension or compression. Always guess tension. And so if you're wrong and get a negative answer, you will know that always means it's actually in compression. So let's start solving this one for that. Well, I have another funny little problem here. This one's on a funny angle. That seems like a pain in the butt to me. This is BX, and this is BY, which we learned a couple weeks ago is how we can break this B force up into its principal axes components. We know that BX squared plus BY squared equals B squared. And we know if we knew what its angle was relative to the x-axis, that would be very helpful as well. Let's maybe just figure that out for our own interest. When we know that each one of these dimensions is 2 and this dimension is 3, and we want to know what it is. So if this is 3 meters and this is 2 meters, we want to know what this angle is relative to the x-axis. We can figure that pretty easily. We know that that's opposite and that's adjacent. And so we know that this angle right here is angle equals the tangent of -1 of opposite over adjacent. So we can solve for our angle. Let's make sure I'm in degrees. I am. Use my second function, tangent, 3 divided by 2. I get that my angle is 56.3 degrees for anything along this line away from the x-axis. So it looks like I now know what this angle is for force B relative to the x-axis. Okay, let's try summing all our forces in the x direction. Everything in this direction is positive, and we want it to be in static equilibrium. We know for it to be in static equilibrium, the system as a whole had a reaction of 25 here. Let's see what we get here. Well, we have A going in this direction, which is positive. We have BX going in this direction, which is positive. And we have C going in that direction, which is positive. And that's all we've got. We've got A plus BX plus C equals 0. So we've got 3 unknowns and 1 equation. We can't solve that. Let's see if we can get anything else here. We have, let's do the sum of the forces in the y direction, where everything upwards is positive. Well, we've got our positive 25 kilonewtons, and we've got By going downwards, or minus By equals 0. Well, it looks like we could solve for By. That's pretty handy. We know that By now equals 25 kilonewtons. And it doesn't tell us what B is. Maybe we could go find what B is, but let's just hold off for right now. Let's sum the moments where everything in that direction is positive about the z-axis, and let's do our same trick where we pick that point right there. We're going to pick RL equals 0. So let's try looking at that. Let's hold our thumbtack right here. C passes through the node. Our 25 kilonewtons passes through the node. Our BX, we've cut this right here, but we could have imagined we cut it just right there. So BX is passing right along this line, BY is passing right along this line, and A is passing right along this line, because B comes right through here. So it looks like we have a few things that could cause this to spin. Let's take a look at that. A is trying to spin it in that direction, or minus A times 3 meters. BX is also along the same line here, because this could all just shift to just this side of the node. So we've got plus BX also times 3 meters. We have BY, which is passing right through this line right here, also trying to spin it in that direction. Oh, sorry, the BX should have been negative here. Minus BX minus BY times 2. All of this equals 0. Those are the three things trying to make it spin, because C, 25, and 0 pass through it. We've got 3 unknowns here, 1 unknown there. One of them is the same. We know these two are related. What if I don't like this spot that I picked? I know solving for reactions, I always picked that node there. Let's try something different. You could still go through this and solve for this. We have the ability to solve this problem already. I'm going to show you a better spot to make the cut. What if, instead of this, we summed the moments about the z-axis with everything in that direction being positive at this node right here? I'm going to call this node AB, right where A and B meet, right there. So I'm going to say, I'm going to spin it about this point right here. Remember from our teeter-totter example, we could pick whatever spot we chose to spin about. Once it's in static equilibrium, it's in static equilibrium. Well, now A passes through this spot, so A doesn't cause it to spin. B passes through that node, which means BX does and BY does. So they don't cause it to spin. We're left with C and 25 kilonewtons trying to make it spin about this point. Let's take a look. 25 kilonewtons is trying to make it spin in this direction, which is the positive direction. Oh, sorry, the negative direction. So 25 kilonewtons is trying to make it spin in this direction. I can use my thumb to tell me that that is negative. So minus 25 times 2 meters. We have C trying to make it spin in that direction. Curl my fingers in the direction C's trying to make it spin. My thumb tells me that that is positive. So plus C times 3 meters equals 0. So we could have picked whatever spot we wanted to spin this about, but this one, I only have 1 unknown now. I made my life a little bit easier. No one says you have to pick the complicated spot. If we can pick whatever spot we want to spin it about, why not pick the easy one? So I am often going to pick it about the node that my element that I break into X and Y goes through, just because it makes my life a tiny little bit easier. Okay, so let's take a look at this now. I can solve for C. C equals so we have 25 times 2, and we bring it over to the other side and divide it by 3. 25 times 2 divided by 3 equals 16.67 kilonewtons. It is a positive value. That means I guessed correctly. That means it is in tension. So C is 16.67 kilonewtons of axial tension. So for this to be in equilibrium, it's like somebody is stretching on this member right here in that direction. Well, let's just take a look at our foam block here. When we tried to bend something, the top was in compression and the bottom was in tension. That seems to match what we expect should happen here on the bottom, that we do have an element in tension. Okay, we figured out what our angle was. Let's redraw that instead as if it was B and BX and BY. And we know that this angle here is 56.3 degrees. Well, we know what BY is, so we should be able to solve for BX, and we should be able to solve for B, because we know what BY is. Let's just pretend I hadn't solved this yet for a second. Remember, we were able to write B as if it was talking about BX and BY. Or if you guys remember, opposite divided by hypotenuse equals the oh my god, I always have to think for a second here for a second. The sine of the angle. Let me just, I want to make sure I'm being consistent with you guys. Yeah, so we're always doing that. Okay, so if we remember, we had opposite over hypotenuse. So the sine of the angle equals BY divided by B. And the cosine of the angle always equaled BX divided by B, if we're always talking about the angle referenced from the x-axis. Or we can say that B just one second, sorry. There's just something happening in the background here for just a second. Sorry. Sorry. Sorry, there's just some weird stuff happening in the background. I'm going to take a drink of water and reset myself before I say any more. Okay. Well, we want to know what BY is, because we want to be able to figure out what that value right there could be. Or basically, I'm showing you a handy trick that's going to make our life a little bit easier. BY equals B times the sine of our angle. And BX equals B times the cosine of our angle. What if instead of solving this, because BY doesn't mean much to me, I know that BY actually equals B times the sine of 56.3. So what if I brought this down here instead and said 25 minus, instead of BY, I'm going to write B times the sine of 56.3 equals 0. Well, now I can directly solve for B. Let's see what we get here if we solve for B now. We would take B over B sine 56.3 over to this side and make it positive, and then we could divide 25 by sine 56.3. So 25 divided by the sine 56.3 equals 30.0 kilonewtons. When I solve for this, I get that my answer is positive. That means it's in tension. Okay, let's come back up to this equation right here. Let's come here to this one where we had A plus BX plus C. Well, A is the only thing we don't know. a plus bx. Well, let's just write this in for bx, because we know bx equals b times the cosine of 56.3. And we already know that c is 16.67. So now it looks like we can solve for a. Let's see what we get. We've solved for b as well, so we can write b in as 30. So we have 30 times the cosine of 56.3 plus 16.67. All right, so both of these are positive, which means they need to come over here and be negative. So 30 times the cosine of 56.3 plus 16.67, and we need to take that over and be negative. A equals minus 33.3 kilonewtons. Well, we have our first negative number. We know that if the number is negative, it means that the direction we guessed our arrow to be in must be the other way. We guessed that this was in tension, or that our arrow went in this direction. It really means our arrow goes in that direction. Or we can say that this is A equals 33.3 kilonewtons in compression. Knowing if something is in tension or compression is very, very, very important. Just knowing it's an axial load does not give us the ability to analyze it or design it later on. We need to know if it's in tension or compression. Okay, so we've taken a look at this one. What happens, and this is always what I get asked, what if we had cut that and kept the other side? What if we did it the other way around? Okay, I'm going to do that very quickly for you, where I'm not going to go through it in quite such intensity because we've done it once now. But let's take a look at what happens if we did that. So let's keep the other half of this truss instead. So keeping the right now. So we're going to do the same thing, but keeping the right-hand side of the truss. Okay, we know that there must be internal loads, and again, even though we've already solved this, I am going to assume everything is in tension. Remember, the arrow pointing away from the cut means tension. The direction doesn't mean tension or compression. It's whether it's acting away or towards the cut that tells us if it's tension or compression. We're guessing that all three of them are in tension. Because we don't know, we might as well have some sort of consistent method. We know that this is 3 meters, and this is 2 meters, and this is 2 meters, and we had solved this previously to know that this was 75 kilonewtons of reaction right there, but when we cut this side, check it out. We also have 100 kilonewtons of load. In the other example, when we cut the other side, we were not saying there wasn't 100 kilonewtons of load. That reaction of 25 kilonewtons is only true because there's 100 kilonewtons of load in the location that it is. So if we're cutting and keeping this side, we need to keep everything that is happening on that side. Well, we've already solved this part of it, so I'm just going to write it here again to be thorough. If this is by and this is bx and this is b, and we've already solved for our angle is 56.3 degrees, we know that by equals b times the sine of 56.3 degrees, and bx equals b times the cosine of 56.3 degrees. So we're going to start to be a little bit faster about this now. So let's jump right into it. I am going to jump right in, and I am going to pick solving this about this node right here. Actually, let's just remind ourselves. This is by, and this is bx. So I've just broken b down into by and bx, just to kind of help keep my mind, things organized here. I am going to spin everything about this node right here. I'm going to do my moment one first. You can do these equations in whatever order you want. So I'm going to sum the moments about the z-axis, where everything in that direction is positive, and I want to know what it takes for this to be in static equilibrium. And I'm going to pick this node BC. So I'm going to put my thumbtack right here. B passes through the node, which means by and bx do. C passes through the node. That's great. That gets rid of 2, if you want to break it up, 3 unknowns that were going to plague me. It leaves me only with an unknown of A. So I put my thumbtack here. A is trying to spin my paper in that direction. Curl my fingers in that direction. It's positive. So I have plus A times, and this node is 3 meters away from where A is trying to pass through. My 100 kilonewtons is trying to spin it in that direction. Curl my fingers. That is a negative. So minus 100 times 2 meters. And 75 kilonewtons is trying to spin it in that direction. Curl my fingers. My thumb tells me that's a positive moment. Or plus 75 times 4 meters. And I want this to be in equilibrium, or the sum of all of these moments to be 0. Well, now I can solve directly for A. A equals, bring 100 over, 100 times 2 over, bring 75 times 4 over. So I've got 100 times 2 minus 75 times 4 divided by 3 equals minus 33.3 kilonewtons. I guessed that A was in tension. I get a negative number. That means A is 33.3 kilonewtons in compression. That is exactly what we got when we did it in the other direction. So it seems like, or when we cut the oven, kept the other side. It seems like it doesn't matter what way we cut and keep things, as long as we keep everything on that side, this will work. Let's now try summing our forces in the y direction. So everything upwards is positive. A is in the x-axis, C is in the x-axis, BX is in the x-axis. Sorry, those are all on the x-axis. I've got BY 175. So plus BY, well, I'm lazy. I'm going to write directly, and instead of writing BY, I'm going to write that as the placeholder for BY. So if you find it helpful, I'm just going to remind us that this is BY. We've got 100 kilonewtons going downwards, and we've got 75 kilonewtons going upwards. We can solve for B. We have 100 minus 75 divided by the sine of 56.3 degrees. We get B equals 30.0 kilonewtons. It's positive, which means that my arrow was correct. I guessed that B was in tension, so it looks like I was correct. B is in tension. And now I can sum my forces in the x direction, where everything in that direction equals 0. 100 kilonewtons and 75 kilonewtons are in the y direction, so they're not helpful to me. By is in the y direction. I'm left with A, Bx, and C. A is going in that direction, which is negative, and I calculated that A is minus 33.3 56.3. I have that C is going in the negative direction, so minus C. And I have BX is going in the negative direction, so minus BX. We know that BX is B cosine 56.3, and we know what B is. So minus 30 cosine 56.3 degrees. If it's helpful, I can remind you that this is just BX. All of that equals 0. There's actually, as complicated as this looks, there's only one unknown here. Let's bring our C over to the other side, so it's positive. A negative times a negative is a positive. So we have 33.3 minus 30 cosine 56.3. So 33.3 minus 30 times the cosine of 56.3, and we get that C equals 16.6 kilonewtons, and the number is positive, which means whatever arrow direction I drew must be right. I drew tension. This tells me I'm right, and so this really is in tension. It doesn't matter which way we did it. We got that A was 33.3 kilonewtons of compression. We got that B was 30 kilonewtons of tension. And we got that C was 16.6 or 16.67 kilonewtons in tension. There's a slight rounding discrepancy there, but they're pretty much the exact same. If we kept more decimals on our angle, we'd have better rounding numbers for this. Don't worry, I build those things in to calculations. Okay, let's come back to this for a second. I'm not going to lift my screen up because we're going to do another calculation in just a second. So we just solved this. Look what I've done here. I have drawn the arrows in the direction that the value was. So we can rewrite this as the internal forces in this. We had C in tension, B in tension, and A in compression. If I draw the arrow in the other direction, I don't need my negative anymore. My negative was just telling me that I was wrong. It was telling me that that arrow should actually be in compression. And remember, an arrow towards the point you've cut is compression. An arrow away from the point you've cut is tension. You can draw this two different ways. You could keep this arrow going away and write this as a negative to let yourself know that you're actually in compression. Both ways are valid, and depending on what we're looking for, we will do it either way. Okay, let's try to find the rest of the forces in this truss. We're gonna get fast at this. We already know what our angle is. Look, all of these are 2 meters wide, all of these bays, and 3 meters tall. So this is 56.3, this is 56.3, this is 56.3, and this is 56.3. That wouldn't be true if we had different dimensions kind of going around this. I'm going to give you a tip. Remember I was saying, do we label this, or do I just labeled cutting through here as A, B, and C, and then I called this node here AB. It's very helpful to just go through and give every member a letter and every node a number. And then you can kind of help start to keep track of things. So we're going to go through and do this, figuring out what the internal forces are for every member in this truss. Okay, so let's solve the truss. I often find it helpful to draw my free body diagram. 2, 4, 6, 8, 1, 2, 3. Like I said, I'm not going to draw it as big this time. We've already solved for the reactions of this truss. We know that this has 100 kilonewtons here, 75 kilonewtons here, and 25 kilonewtons here, and 0 kilonewtons here. I am going to go through and label this A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. So all of my members are labeled. I am now, I wonder if I can get this. I can't get it any closer for you guys. Maybe. Oh, sorry, if I fiddle with it too much, it moves around a bit. I'm gonna move my chair. Okay. I'm also going to label my nodes. I'm going to call you 0. I'm going to call you 1, 2, 3, 4, 5, 6, 7, 8, 9. There is no right way to labeling this. You could call them Adam, Bob, Charlie, Dick, Aaron, Fred, Gina, Hal, Irene. It doesn't matter. You could call them Larry, Curly, and Moe. It doesn't matter. This is just about bookkeeping. I like to do this because I then like to write myself a little list here about what all of these forces are. So A equals B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. And we want to know what all of these internal forces are. That's what we're setting out to do here. Well, check it out. We originally cut right here. We cut through K, D, and O. We called them A, B, and C because we didn't know what we were doing, but we cut through K, D, and O. And we established that this member here, that is K, was actually 33 kilonewtons of compression. So let's go find our K. 33.3 kilonewtons of compression. We found that our member D, which was previously what we were calling B, is 30 kilonewtons of tension. It had 30 kilonewtons of tension in it. Member O, which we were previously calling C, had 16.67 kilonewtons of tension in it. So O is 16.67 kilonewtons of tension. Whew, we have a lot of things to solve still. So let's go quickly. Let's do our first free body diagram. I am going to do a section that cuts through A and N. So I am going to call this A, N section. Now let's check it out. I am going to draw node 0 here. I've got cutting through A and I'm cutting through N. I'm going to draw my unknown A in tension and my unknown N in tension. And I know that I had 0 kilonewtons here and 25 kilonewtons here. Let's start solving. Let's solve for the forces in the x direction, with everything that direction being positive. We have N plus 0 equals 0. So N equals 0 kilonewtons. Great. We've solved our first one. Sum of the forces in the y direction equals 0, where everything upwards is positive. We have A upwards plus 25 kilonewtons going upwards equals 0. A equals minus 25 kilonewtons, or A equals 25 kilonewtons in compression. We can fill that in. All right, well, that wasn't too bad. That next section really kind of gave us some good answers. Let's cut through J, B, and N. n. So let's do J, B, N. Oh, sorry. Is that what I want to do? Yeah, let's do J, B, and N section. Okay. All right, we know that this is 3 meters tall. We have 25 kilonewtons here and 0 kilonewtons here acting on this. We've already solved for n. N equals 0. We don't know what B is, and we don't know what J is, so I'm going to draw them both in tension because I don't know. I've got BX, and I've got BY, and I know, based on my angles, that BY equals B times the sine of 56.3 degrees, and BX equals B times the cosine of 56.3 degrees. So we can just plug these in for anywhere we see BY or BX. So let's start by summing our forces in the, let's do the Y direction first. Doesn't matter, we can do it in whatever order we feel like. So I'm going to sum the forces in the Y direction where everything upwards is positive. We've got 25 kilonewtons upwards as our reaction, and we've got BY going downwards. So minus BY is going downwards, and BY is B sine 56.3 degrees. Those are the only things going up or down. Those are the only things in the Y direction. But it looks like we can solve for B. All right, let's take this over to the other side. So we've got 25 divided by the sine of 56.3 degrees. And we get B equals 30 kilonewtons. Our value is positive, which means it's in tension. So we've solved for B. Guess what, guys? We had actually already solved for B. Look at that. We didn't need to do that one. We had already solved for B. It was a known for us. So, good for us. We've already done it. No, that doesn't. Do you know what I did earlier? I apologize. When I wrote D in, we had solved it before where that member was B, and that was supposed to be 30 kilonewtons of tension. We didn't know what our new B was, and it does happen to be the exact same value. So great, we did need to solve this, and we have it is also 30 kilonewtons in tension. That's interesting. Both of those have the same value. Cool. Okay, let's move on. Let's sum the forces in the X direction. So we already know N, we know B, J is our only unknown now. So let's sum our forces in the X direction. N is 0, 25 goes up and down. So we have J and BX. Okay, so J is in the positive direction. BX is in the positive direction. We know that BX can be written as B cosine 56.3, but we've already solved for B. So 30 times the cosine of 56.3 degrees equals 0. We can solve for J. J equals negative 30 times the cosine of 56.3, or minus 16.6 kilonewtons. Our answer is a negative. That means it is 16.6 kilonewtons of compression. So we can write that in J. 16.6 kilonewtons of compression. Okay, let's do another cut. That one was through J. So we have A, J, B, and N. We already know K, D, and O. I am going to do one through L, F, and P now. You can do these in whatever order you want. So I'm going to do L, F, and P now. So 3. We now have this member here like this. So this is, we don't know what any of these values are, so I'm going to draw them all in tension. L, F, P. I'm going to draw F as Fx and Fy as my unknowns. And we have our reaction 0 and our reaction of 25 kilonewtons. That is only true because we know we have 100 kilonewtons applied over here somewhere. We know that Fy equals F times the sine of 56.3 degrees, and Fx equals F times the cosine of 56.3 degrees. Let's start solving some of these equations. Let's do it, let's solve for up and down. So sum of the forces in the y direction equals 0, where upwards is positive. We have 25 kilonewtons upwards, which is positive, and we have Fy, which is upwards, drawn upwards, so it's positive. Fy we know is F sine 56.3. And that's the only thing going in the up or down direction. Sorry, I just want to very delicately move a cord here without moving anything. Okay, and then let's rearrange this, and we get that F equals negative 25 divided by the sine of 56.3. F equals minus 30.0 kilonewtons, or F equals 30 kilonewtons of compression. I had guessed that it was in tension. A negative number tells me that whatever I guessed was wrong. So I guessed tension, that means it's actually in compression. So F equals 30 kilonewtons of compression. So I've just filled that in to my chart. I am now going to try to spin this about this point right here. Why that point? That's the point I feel like. I'm going to pick point 4. I'm going to tell you that I'm pretty good at doing this, and I can see at a glance that it is going to cut out for me a bunch of things that I don't want to have to solve for. I am going to be able to get rid of F, which means Fy and Fx. I'm going to be able to get rid of P. I will be left with 25 kilonewtons and my L. Do you know what I didn't do here? I didn't draw my dimensions. A free body diagram always needs its dimensions. Okay, let's try spinning this section about that node right there. Let's sum the moments about node 4, about the z-axis. Everything in that direction is positive, And we want to know what it takes for this to be in static equilibrium. So we're going to put our thumbtack right here. We know F passes through it and P passes through it. It means we're left with 25 kilonewtons trying to spin it in that direction. My thumb, curling my fingers of my right hand in the direction it's trying to spin it, my thumb tells me that that is a negative number. So minus 25 times, and it is 4 meters away. L is trying to spin it in that direction. Curl my fingers in the direction it's trying to spin. It tells me it's a negative moment, so minus L times the closest it comes to it is right along this path. It's acting in this direction right here. So the closest it comes is 3 meters. I can rearrange this and solve for L. I end up with negative 25 times 4 divided by 3. I get minus 33.3 kilonewtons, or L equals 33.3 kilonewtons in compression. Let's write that in our chart. 33.3 kilonewtons compression. Look, we're slowly filling up this chart. We're doing pretty good. We still have one more unknown we can solve for here. Let's solve for P. Let's sum our forces in the x direction, where everything in that direction is positive. We have L going in that direction, which is positive. But we've solved for L, and we know that it's actually going in the other direction, or it's a negative value. It's in compression. We have our Fx, which is going in that direction there. You know what? I'm gonna write this over here because we're gonna need a little more room. So plus, so our L, we've drawn our arrow going in our positive direction, but we've solved for it and we know it's a negative 33.3. We could come back and redraw this arrow going in that direction and use a positive 33.3. Then we would have a positive 33.3 going in that direction. Either way, we would get the same value here. We have Fx going in this direction, which is positive. Fx can be F times the cosine of 56.3, and we've solved for F, and we know it's minus 30. And then we have P also going in the positive direction. So we can now solve for P. We have 33.3 plus 30 times the cos of 56.3 equals, I'm going to round this because I know that had I kept more significant digits here, P equals 50 kilonewtons. You could actually keep more than 56.3. You could keep more than the 3 there. You could go a little bit further over. I get 50 kilonewtons positive. I assumed it was in tension. Getting a positive value means I was correct, and it is in fact in tension. I can fill this into my chart now. So P equals 50 kilonewtons of tension. All right, so that cut through L, F, and P. Let's cut through M, H. Let's cut through M, H, and Q. M, H, and Q section. Okay. Now, you could always cut this from the other direction. I like to be consistent and always keep this side, mostly because I'm lazy and I like to make sure I have a consistent method so that I don't mess up. We know that we have 2 meters, 2 meters, and 2 meters, and 3 meters. We know that we've solved for this, and we have 25 kilonewtons here and 0 kilonewtons here. We know that we're cutting through M, H, and Q. Oh, that was M. And H we're going to break down into HX and HY. But we also now are cutting past the point where our 100 kilonewtons shows up on our truss. Remember, you have to keep everything on the side you're cutting. When we did our cut through here, we showed everything that was on this side, but then when we did it and showed everything on this side, we had our 100 kilonewtons. So we've cut and we're ignoring everything on that side, and we want to figure out what it takes for this section to be in equilibrium, because this section must be in equilibrium because this 25 kilonewtons here and that 100 kilonewtons there on the system we're looking at is in equilibrium. It must be. We've already proven that. So we know that HY equals H times the sine of 56.3 degrees, and HX equals H times the cosine of 56.3 degrees. So we can go through and start solving this now. Let's solve for our forces in the y direction. So sum of the forces in the y direction equals 0, where everything upwards is positive. We have 25 kilonewtons going upwards. We have 100 kilonewtons going downwards. And we have HY going upwards. So plus HY, we know that HY is H sine 56.3 degrees. We can solve for H. All right, so we have 100 minus 25 divided by the sine of 56.3 degrees. And we get H equals 90.1 kilonewtons. The answer is positive. I guessed that H was in tension. Positive answer means I guessed right, and that means my value is in tension. We can fill that into our chart. H equals 90.1 kilonewtons of tension. Okay, let's now, I'm going to sum the moments about this node right here, which is node 6. So I am going to sum the moments about the z-axes in this direction with everything, the sum of all of those needing to be 0, and I'm going to pick node 6. If I pick node 6, H passes through it, which means there's no moment. Q passes through it, which means there's no moment. 100 kilonewtons passes through it, which means there's no moment. It means 25 and M are the only things causing it to spin. So if I put my thumbtack here, M spins it in that direction, and 25 spins it in that direction. Both of those are negative. So we have minus 25 times 2, 4, 6 meters. And we have minus M times 3 meters. M equals minus 25 times 6 divided by 3 equals minus 50 kilonewtons. Well, a negative means I guessed wrong. I had guessed that M was in tension. That means M is really in compression. I can fill that into my list. Whew, okay, I know this is long. We still have a few more math problems to solve here too, so I'm trying to be quick. Okay, let's move on to the next one. We are going to cut through N, B, C, and O. So I'm going to cut through N, B, C, and O. Basically, I'm going to draw everything at node 2. So, N, B, C, and O section. So I've got this node right here, and basically we're drawing at node 2. So node 2 is right here. All right, we had, acting on that node right there, we have C, we have, let's draw all our arrows in, N, B, C, and O. Let's just look if we know the values of any of these. Well, B, we know equals 30 kilonewtons in tension, which we've drawn. N equals 0. C we don't know. And O we know equals 16.67 kilonewtons of tension. And we've drawn it in tension. Well, that works out pretty well. We have BX and BY. We know that BY equals B times the sine of 56.3 degrees, and BX equals B times the cosine of 56.3 degrees. So let's start solving for these forces. The only thing we don't know is C. So sum of the forces in the y direction equals 0, where everything upwards is positive. We have C going upwards, and we have BY going upwards. BY is B sine 56.3, and we know what B is. B is 30. We can solve for this, and we get that C equals 30 times the sine of 56.3. C equals minus 25 kilonewtons. If something is a negative value, it means I drew my arrow wrong. I guessed it was in tension. That means C equals 25 kilonewtons of compression. Let's fill that in. 25.0 kilonewtons of compression. Let's do another one where I draw it at a node. So let's cut through OD. Oh, no, I'm going to cut it through K, E, and L because I am lazy. So K, E, and L section. I don't have E. Right. So let's draw that node here, which is node 5. All right, let's draw our internal forces here. I'm going to draw them all. in tension, and then use a negative value if it means I'm going in the other direction. And this was K, E, and L. K, we've already solved, is 33.3 kilonewtons in compression. So I'm going to indicate that that's actually going in the other direction with a negative value. L, we've already solved, is 33 kilonewtons in compression, so minus 33.3 kilonewtons. Basically, instead of two arrows going, that direction of 33.3 kilonewtons, we have two forces both pushing in on this node with 33.3 kilonewtons of compression. There's nothing else acting here on this. The sum of the forces in the y direction, where everything upwards is positive, E equals 0. Well, that one was nice and easy. E equals 0 kilonewtons. Let's do okay, let's cut through P, G, H, and Q. We know P, we don't know G, we know H, and we don't know Q. So maybe we can solve for something here. So let's do P, G, H, and Q section. So we've got a node here that's got G, H, Q, and P. I'm going to draw them all in tension right now. P, G, H, and Q. We've already solved for P, which is filled 50 kilonewtons of tension, and we've drawn it in tension. Q we don't know. H we know is 90.1 kilonewtons in tension. And G we don't know. We know H can break up into HX and HY. I'm going to stop drawing the little summary of what that means. Actually, we already drew it up here, that HY and HX, that's what we can break it up into. Let's sum our forces in the X direction. So sum of the forces in the X direction equals 0. We've got 50 kilonewtons going this way, so minus 50 kilonewtons because it's moving in that direction. We have HX going in this direction, which is positive. We know that HX is H times the cosine of 56.3, and we know what H is. So 90.1 times the cosine of 56.3 equals 0. And, we also then have plus Q, which we don't know what it is, equals 0. Those are the only things moving in the X direction, P, Q, and HX. Let's solve for Q. So 50 kilonewtons minus 90.1 times the cosine of 56.3 equals essentially 0. So Q equals 0 kilonewtons. We have G still that we can solve here for, which is going up and down. Let's sum our forces in the Y direction. Everything upwards is positive. 50 goes in that direction, Q goes in that direction. We have G going upwards, and we have HY going upwards, which is positive. So plus HY, we know that HY is H sine of 56.3, and we know what H is. We know it's 90.1. Those are the only two things going in the up and down direction. So we can solve for G. G equals the negative of 90.1 times the sine of 56.3, or minus 75 kilonewtons, or G equals 75 kilonewtons in compression. So G, 75 kilonewtons of compression. We have one thing left we don't know, one more section to solve for. Let's cut through Q and I. So let's cut through there, Q, I. We have at this node a reaction of 75 kilonewtons. We don't want to forget that. I, we don't know what it is. I is what we're still looking for. But Q, we already solved, equals 0. Oh, this one looks nice and easy. Sum of the forces in the y direction where everything upwards is positive. We've got plus I plus 75 equals 0. I equals minus 75 kilonewtons, or I equals 75 kilonewtons in compression. Let's fill that in here. We now know that for this particular truss, we know what the reactions are that keep this thing in static equilibrium. And for it to be in static equilibrium with these reactions, these must be the internal axial forces of all of the elements in this. If this 100 kilonewtons was a factored load, we now know all of the internal factored axial loads in this truss. If we wanted to make sure that we met life safety requirements, we know that our reduced capacity of whatever these members are has to be greater than all of these internal factored loads. It looks like we finally have something to check against. So let's come up here. We'll turn this to me. Okay. So we've done this. I'm trying to decide if I should do this right now or not. I don't want to make this lecture go too long. I have lots of bonus examples worked out for you guys. Let me just go through quickly. Okay, I'm going to do this one. No, I have these. I'm going to talk this one through. I'm not going to work it out with you guys because we have it all worked out here. So this truss right here, we have, it's actually a braced frame. If you guys remember, I talked about how if we had this sitting here like this and we put a load on it, it would try to collapse. It would flop over. If we put this brace element in it, when we try to push on it, it doesn't try to tip over. Or if we push on it on this side, it now doesn't, unless it breaks. But we needed this here. You can see that this slipped out of here. It was in tension. And I think intuitively you understand that, but we need that element to stop this whole thing from collapsing. So this is called a lateral load resisting system, and this would go in the wall of our building. This particular one is a braced frame lateral load resisting system. We're pushing on it at this corner with 250 kilonewtons. We have this system supported right here. They're 8 meters apart and 5 meters tall. We can solve for the reactions. The only problem is we don't know, these both are shown as pins. We would have two different reactions here in the x direction, which isn't something we've dealt with so far. So we would have L y and ry, lx and rx. So when we go through and solve these reactions, we would end up solving, let's look at it this way. So step 1, we solve for the reactions. Sum of the forces in the y direction, we have ly up and ry up, and nothing acting downwards. So ly is going to be the negative of ry. That's all we know. We don't know what their value are, but they're going to be equal and opposite. What do we know about something that is equal and opposite? That's a couple. Interesting. It looks like this is kind of what stops this from tipping over. Let's sum our forces in the x direction. Well, we have Lx in this direction and Rx in this direction, and we have 250 kilonewtons in the negative direction. It doesn't look like there's much more we can do with that. We've got 2 unknowns here. Okay, we have one more equation that we can use. We can sum the moments about a node. I'm going to sum them about this node right here. So that means Ly goes out of the equation, Lx goes out of the equation, and Rx goes out of the equation. All we're left with is Ry. Ry tries to spin it in this direction about node 0. Our 250 kilonewtons tries to spin it in this direction about node 0. So we can write that all down, and when we rearrange it, Ry equals minus 156.25 kilonewtons. Or Ry equals 156.25 downwards. I guessed it was an upward arrow. That negative value means I'm wrong. Well, we knew that Ly equaled the negative of Ry, so Ly is 156.25 upwards. So as 250 kilonewtons tries to push to tip this over, one side pushes down and one side tries to pull up with an equal and opposite force of 250 or 156.25 kilonewtons. We still don't know Lx and Rx, but let's just start cutting sections. Let's cut our first section right here at A and D with 250 kilonewtons on it. So you can see here we've got A and D drawn in tension and our applied load. Well, the sum of the forces in the y direction, D, equals 0. Okay? The sum of the forces in the x direction, A, equals 250 kilonewtons of compression. So, easily, we've already got A and D. There's only 2 more unknowns in this, but also our Ry, our Rx, and our Lx. If D equals 0, let's go back to that free body diagram here, where we have Ry downwards, D upwards, but it's actually 0, and our Rx in this direction. We can find the angle of B. We know that the dimensions of this frame were 5 meters tall by 8 meters wide, so we can find that that's an angle of 32 degrees. Again, this is all worked out here. You can go through and try this on your own. I'm just trying to talk it through to help you out. I'm trying to speed it up a little bit, but yet give you all the information. I don't want to leave you short on examples for the people that are ready to move on. Okay, let's sum the forces in the y direction. We've got D upwards, we've got BY going upwards. We know D is 0 and RY going down. We know what RY is, so we can solve for B. B equals 295 kilonewtons in tension. Remember, BY equals B sine 32 degrees minus our 156.25 kilonewtons downwards. We can solve for B. The sum of the forces in the y direction, Rx in this direction, Bx in that direction. We know what Bx is. Bx is B cosine 32. We've solved for B is 295. We can solve for Rx. Rx equals 250 kilonewtons. Remember from before, we had some equation that had Lx plus Rx minus 250 kilonewtons. Let's plug the 250 kilonewtons for Rx in. Lx equals 0 kilonewtons. Let's do one more free body diagram where we cut through this section right here, which I believe was C. Yep, let's cut through section C. The sum of the forces in the y direction, we know Lx is 0, we know Ly is 156.25 kilonewtons. We solve for this, and C equals 156.25 kilonewtons. Let's just write out everything we know here. We have our reactions. So this one's going up and this one's going down. Our reaction to stop it from sliding is all happening right here. We have 0 force in this member. We have 250 kilonewtons of compression here. 295 kilonewtons of tension in the brace, and 156.25 kilonewtons of compression right here. So remember when I pushed on this, for you guys so it looks the same, when I pushed on this right here, if I pushed really hard, I actually had this in tension and I slid it out. Nothing else failed. Well, it does seem to make sense that this is the highest value and it's in tension. Kind of seems to match what we saw here. Also, when I do it, this tries to push down and this side tries to lift up. So it's matching what we're getting as our reactions here. Now, the numbers are helpful, but drawing things can be really extra helpful, I find. So let's talk about what an axial force diagram is. So if we have a value of 200 kilonewtons coming down on this, we have a roller and a support here. We're saying that we have 200 kilonewtons of force all the way through the length of this member. We could draw our free body diagram. Actually, first, let's solve for our reactions. Well, the sum of our forces in the y direction, if this was our reaction in the y direction, would be 200 kilonewtons. That makes sense. We're pushing down with 200. We've got to be pushing up with 200. If we cut through here at any spot and drew our unknown as a tension, we would find it was actually a negative number telling us it was 200 kilonewtons of compression. So we're saying that anywhere along the length of this member, we have 200 kilonewtons of compression. What would happen if we had 200 kilonewtons pushing down here and 300 kilonewtons pushing down here? Well, pushing up right here, we have 300 plus 200. We must be pushing back up with 500 kilonewtons of force. If I cut right here and only kept the top, my unknown force right here would be 200 kilonewtons of compression. If I cut right here and only kept the top, I have 200 and 300 pushing down. Pushing back up, I must have 500 kilonewtons of compression. If I cut right here and only kept the bottom with 500 kilonewton reaction here, I would have to push down with 500 kilonewtons or 500 kilonewtons of compression internally in that element. We would say that anywhere along this portion of it, we have 200 kilonewtons of compression, and anywhere along this portion of it, we have 500 kilonewtons of compression. Let's draw the axial force diagram of our truss. Now, it was really messy to draw the chords in, the webs in, so I'm just drawing the top chord and the bottom chord for you, just so it's a little bit easier to see. So these were the values we figured out. Look, there's all compression in the top and all tension in the bottom, and it looks like these two members are the most impacted. Let's draw the axial force diagram of our frame. We had nothing in this one, 250 kilonewtons of compression, 156.25 kilonewtons of compression, and 295 kilonewtons of tension. So these visual diagrams are very handy to see at a glance which one's working the hardest. I will often do compression in one color and tension in another to also aid me. You know what, before I post this, that's exactly what I'm gonna do for you guys. I'm gonna change compression and tension colors for you. All right, let's do another cool thought exercise. When we looked at our truss with some unknown forces, we know that when we're bending this element, the top is in compression and the bottom is in tension. When we did it with our truss, we saw that we had the top in compression and the bottom in tension, and then we had a web element with some diagonal component to it. We, being lazy, broke that down into X and Y components because that made our life easier. So we can rewrite that as our X and Y components. Well, what if we then, since we know that we could have cut this right there, let's just bring that X component down here to this X component. So it's really the same thing. Well, look at this. We've got this force going up, and we have equal and opposite forces. What do we know about equal and opposite forces? They can be written as a moment. So if we wanted to take the compression in the top chord and the tension in the bottom chord, if they were equal and opposite, and write it as a moment, if we were talking about a beam and this is what it looked like, we could, instead of looking at a top chord and a bottom chord, we could write that as a moment. What if then these were our internal unknown elements? This is our shear and this is our moment. We now have two different unknown internal elements. So axial forces in the top chord, bottom chord, and web element of a truss can be rewritten as a shear force and a bending moment. That's going to be really handy when it's not chorded elements or simple, built up out of small, simple elements. This is going to be handy for something like this. If I'm bending it and I know it's in equilibrium, I should be able to cut it here and figure out what the internal shear and bending moment is. So remember that bending, putting a component in one side in tension and the opposite in compression, and we could rewrite that as a couple. That's exactly what we're going to do now. Okay, so I just went and looked at everything I was trying to throw at you today. I don't like it. I think it was too much and not fair. So I'm going to cut today's lecture into two separate lectures. We're going to pause where we just were in that lecture, and I'm going to turn that into next week's lecture. And so I'll reshuffle things a little bit, and I'll combine concrete at the end of the term or the second last lecture into one lecture. So I'll go through and update that, and I am now going to go revise your assignment and quiz because they were based on this being a full lecture. So I have a little bit of reworking to do very quickly for you guys. That said, I think this is a much better kind of breakdown of information. It felt wrong throwing so much at you guys right in probably when you're in quite an anxious point of time in the term. You're just trying to get it all figured out. And some of your stuff is probably back in person, which adds a whole lot of stress to it. So I'm going to spend the next few hours kind of sorting that all out. But for you guys, this week was method of sections with trusses, braced frames, and looking at axial force diagrams. And that's going to be what we have talked about today. I'll move on to method of sections with beams for next week, which talks about shear and moment, and maybe build in a little bit of axial as well. So your takeaway tips for today then are, if we know the forces, we can use the free body diagram to calculate the reactions because it needs to be in equilibrium. That's what we learned last week. We know if the forces and the reactions, we can use this is a weird line. If we know the forces and the reactions, we can use the free body diagram of the part or use method of sections to calculate the internal forces that have to be in that object to keep it from moving up and down or back and forth or spinning about in space. So remember, we're figuring out the forces. That's what we figured out in the first few weeks. We figure out the loads on the building, and then we take the tributary area and we apply the load to the object. If we've done that, we can figure out the reactions that must be there to keep it in equilibrium. That's what we want. We want it to be in equilibrium, and we want to design whatever it takes for it to be in equilibrium. If it's in equilibrium, that load has to be getting from its applied location to its support location, so there's something internal happening. And that's where we understand if the object isn't moving, the part can't be moving. So we cut it into parts and try to figure out, using the same equations, what our internal forces are. So then we can do method of sections for our truss analysis. Once we know what all of our internal axial forces are, we could draw ourselves a nice, beautiful axial force diagram. And next week, we'll see how that applies to shear and moment.